In the previous video, we talked about multi-input, multi-output open loop system, time invariant. Alright, time invariant doesn't change with time. So now we're going to talk about the closed loop system. Alright, in order to derive the closed loop system, we're going to first understand using back this equation. This is your standard state space system. Alright, next step we're going to do is your standard way of doing is to change your x dot t into dxt dt. Alright, so far so good. These are all the stuff with your boundary conditions saying that at time 0 your x is equals to x naught, where your x naught may be 0, maybe 1, maybe 2, whatever numbers you want to indicate. Alright, and therefore instead of changing your xt now, previously we actually change our xt and things like that. Instead of differentiating, Laplace transform this thing and then sub it into your cxt, we are dealing with the ut now. Previous video we Laplace this one, right? And then we sub it into our xt. In this case, we're gonna do with the ut itself. Okay, so in order to do with this ut itself, you have to first understand the closed loop system. Alright, the closed loop system, as you can see over here, is that you have a closed loop from, you know that closed loop is going in this direction. Okay, and therefore it's simply the x times minus k. Alright, where x is simply the output from your this stuff over here. This is some transfer function. Alright, once you output, you're outputting x. Okay, so x times minus k is equals to your ut over here. So this is why minus kxt, which is k times minus k, x times minus k is this one, equals to your ut. So this whole feedback system goes to your ut. Alright, this tells us that your input, right, to this certain transfer function over here is this one. And therefore what we can do is simply to sub back into our ut. Alright, so this ut, this whole stuff over here, I actually bring it down. As you can see, I've done everything because I have redo and redo. Anyway, so so now axt is plus but, right? So we know that ut is simply kx minus kxt, right? It's over here. So I'll just simply sub in my ut as this one over here. And what we have is this thing. You factorize out the xt and the xt over here. So you have xt and the rest is just a minus bk. Alright, so it's over here. So this thing over here is simply your this stuff shown over here. And it's also equals to your dx over dt. And then this is your initial condition also. Alright. And then this a minus bk over here is simply our ACL closed loop. Okay? Because why? Just now what we have drawn over here is that a closed loop comes back to u. Okay? This may not come naturally, but this is in fact a feedback system. This feedback tells you that u is over here. Okay? If you are talking about a certain transfer function, like let's say g of s is equals to y of s over u of s. Alright? So u of s over here is a denominator. And you know that the denominator is called the characteristic equation. Alright? And in our case, from the previous video, we say that it's a Diophantine characteristic equation is Diophantine ACL. Alright? And therefore we can simply say that ACL is equals to our a minus bk, and we know that this a minus bk is the so-called the denominator of your transfer function us, because as you know it's u in ut or whatever. Okay, but I just want to convey to you is that don't be somewhat misled by this whole chunk over here, this big transfer function, because somewhat talking about having a ax plus a bu. Alright, so this is a parallel system, and if you do generalization, you will have a system like this. Alright, because ax plus bu, you can do it as a parallel block diagram. So this ax over here, alright, is actually coming from your I should have didn't draw like this, I should have drawn this like this. So ax comes from your input. Alright, ax comes from your input. Alright, and it add up with your feedback system. Feedback system comes in as a u, so it acts in a ut also over here. So in this case, this whole transfer function telling you that your current input, what you put into now, alright, add up with your previous feedback system, you have a certain output again. So you're somewhat taking your input, minus away whatever information in the past to tell you that you should do left or do right or do up or do down, alright, whatever thing, just the feedback to you telling you that you should do use your input wisely and things like that. So therefore, don't be confused with all the notation of all this. Just need to know that this is the closed loop system as your input, and this input is being sub back into your BU over here. Alright, things like that. Alright. Therefore, since we know that A minus BK can be re-represented as ACL, alright, and therefore we can simply write this equation as this equation. Alright, dx dt is the same over here. Then A minus BK is equals to ACL, so I'll just sub in as ACL xt. So xt is the same thing over here. Alright, or the boundary conditions are the same. Okay, I didn't share a feeling. Okay, while the yt itself, just leave it there like this. Will do. Alright, because normally the d is equals to 0. Alright, so it should be fine. Alright, but I don't know why it's 0, but just take it first. Okay, and then if you were to Laplace transform your this stuff over here, is pretty straightforward. Will be with this thing over here. This is for this case. So if you Laplace transform dx dt, you have x as x minus x0 s, yeah. So ACL is simply some constants times xt. So xt is changed to xs. Alright, so we're gonna group. Alright, since we know the xs and xs over here are somewhat the same, so I'll just bring this x0 over to the other side first, and then I'll bring this ACL over this side. So what I have is xxs minus ACL xs is equals to x0. So I'm just simply switching the sides only. Then I factorize out my xs, alright, over here. Alright, and then we know that we are multi-variables, so s is simply instead of just s itself is si times a certain identity matrix. Alright, so we're going to re-represent xs as in terms of this thing. I mean in terms of whatever, because now this is a matrix. So what we can do is to inverse determinant. Not inverse determinant, but rather than switch sides. So if you switch sides, you'll have si minus ACL minus 1. Okay? And therefore your xs is equals to this thing. Then now I'm going to Laplace transform this one. It's simply straightforward. SS is equals to this thing. Okay? And since we have found our xs already, then we just sub it in over here. So your y will be equals to c times the x0 and then si minus ACL minus 1 plus dus. Alright. Alright, as you can see, this is very familiar with what we have done just now. We find our xs first, and then we sub in into the cxs plus dus type of thing. Alright. So therefore this is something that you may need to understand. And therefore we know that ACL is equals to A minus KB. Alright, so what I can do is to just rewrite, and we know that D normally is set to 0, so this whole thing becomes 0, so to speak. So I have CX0 and then SI minus, this is ACL, so it's A minus, you can write as KB. Alright, this whole thing minus 1, alright, is your YS. Okay, so you have represents your output as this thing over here already. Okay, so it's a chunk of stuff. Because normally what we want to know is the multi-input. This is multi-input because it's SI with a lot of variables. So you want to know what is the multi-output YS, and therefore you're gonna use the determinant, and then you're gonna find your S, this piece over here. So once you find your determinant, you will have your output over here. Alright, things like that. Okay. Today we'll talk about other stuff, and then I'll just go on to continue this. The other stuff is very straightforward. 1 minute will do. So I'll see you in the 1 minute later.